Hello, welcome to this clip about the prediction of the lean meat percentage of a pig carcass. This is actually a case study you're going to work on. The lean meat percentage of a pig carcass is used for payment towards the farmers. The problem is that if you determine the lean meat percentage, you have to dissect the carcass in lean meat and bone, and after that you can only make meatballs from the carcass. If you have a nice ham in the carcass, you can earn a lot of money, but not when it is totally destroyed. So the measurement is destructive, very expensive as well because it takes hours. So in the slaughter line, the lean meat percentage is predicted, and the predicted lean meat percentage is used for payment towards the farmers. And of course the prediction has to be accurate, otherwise it wouldn't be fair towards the farmers. How does it work? Well, in the Netherlands we use a probe. The probe is an instrument with a long needle, and the probe is inserted at a particular position at the carcass. The needle goes in and it passes through the fat layer and the muscle underneath. And when it is pulled back with a light ray from a small window at the end, the muscle thickness and the fat thickness are being measured. Two measurements for prediction, but we're only going to use one of them in this case study, the fat depth, which is the most important one. So Y in the story is the lean meat percentage of the carcass that we want to predict, and X is the explanatory variable, the predictor. It's the fat depth at a particular position. Now, to predict, you need a prediction formula, and therefore you need to perform a dissection experiment. So a sample of carcasses is collected from Dutch slaughterhouses. Each carcass is measured with the probe that gives us the X, and then it is completely dissected, that takes hours, to get the lean meat percentage, Y. Next, from the data, a prediction formula is calculated, and finally, the accuracy of prediction is determined. Now here, for instance, you have 10 carcasses. In reality, we have more, like 120, but 10 is nice in a plot. So Y against X, you can see that if we fit a line, it will have to go down. It will have to go down because the fatter the carcass, the less meat. 68.3 is the estimated intercept, and minus 0.8 is the estimated slope from least squares. So if you have a new carcass, which is not dissected, and where we only have fat depth, let's say 15 millimeters, we plug in the 15 millimeters in this expression, and out we get is the prediction 56.3%. Now, you cannot use any old prediction formula in a region or a country in the European community because certain regulations have to be met. There are conditions related, for instance, to good statistical practice. How are your carcasses collected? They should be in some sense representative. How is your prediction formula determined? It can be done by least squares, but sometimes people have more complicated instruments or use more complicated methods, and they have to be statistically sound. There are also conditions that relate to the quality of prediction. Is the error of prediction small enough? The error of prediction actually relates to two sources of variation. One of them is estimation error of the intercept and slope. That relates to sample size, but also to the way you collect the carcasses. If you have large variation in fat depth, you can fit the line much easier than when you have small fat depth variation and all the carcasses are bunched together. So the design is important as well. And finally, the predictive value of the explanatory variable, the fat depth in this case, corresponds to a sigma square, a variation around the line, and sigma square should be small enough. When it is not, you need to find other predictors from the carcass that work out better. Well, enjoy your exercise, and just in case that one of you is a vegetarian, I apologize, and I hope you are prepared to work on this case study anyway.